Okay, let's do a couple more examples because these at least one probabilities are a little bit confusing and they take a little bit of practice. So in this case, we have a card is drawn from a standard deck of 52 cards and then placed back into the deck. This is repeated 3 times. Find the probability that an ace is drawn at least once by the third draw. So the first thing that I notice here is that we are placing these cards back into the deck, which gives us independence because we're putting it back in and I'm assuming shuffling here. And so what I choose the first time has no bearing and no effect on what I would choose the second time or the third time. Independent draws. So we are looking for the probability of at least one ace. And we know from our at least one probability rule that this is the same, or to calculate this, we do 1 minus the probability of no aces. And this would be like saying 1 minus, if there are no A's, no aces, that means that the first is not an ace, and the second is not an ace, and the third is not an ace. That's how you get no aces. The first is not, and the second is not, and the third is not. So we've got an and probability here. Because they are independent, that's important. Like this part right here cannot be understated. That's very important. Because they are independent, when we're doing an and probability, we know we're multiplying. So not aces. There are only 4 aces in a deck out of 52 total. So that means there are 48 ways to get anything other than an ace. So the first not being an ace, probability is 48 out of 50. And we'll multiply 48 out of 52. Can't count there. 48 out of 52 cards times 48 out of 52 again times 48 out of 52 again. Okay, and then when you multiply that all out, it's a very, very, very large number. 48 times itself 3 times is 110,592 on the top, and 52 cubed is 140,608. So you're doing this subtraction, you're doing 1 minus this very big fraction. That fraction does reduce, so you're having 1 minus. If I reduce that fraction, it reduces to 1,728 over 2,197. And then subtracting 1 minus that fraction, the best that it'll reduce to is 469 over 2,197. It is not very pretty as a fraction. So if we want to look, possibly they may ask you to give that one as a decimal since it's such a gnarly fraction. And if they were to do that, we could go ahead and divide that out. And so it's approximately, depending on what value you're supposed to round to, approximately 0.213. This is about a 21% probability that after 3 draws, you've drawn an ace at least once. All right, our last example says 2 light bulbs are selected from a batch of 24, of which 4 are actually defective. Part A says, what is the probability that both selected are defective? So if you've got a box of 24 light bulbs, 4 of them are defective. What's the probability that when you randomly select 2, you get 2 defective ones in that selection? The first thing, the first thing that I notice here is that we are selecting these bulbs. There is no order to this. We are just choosing light bulbs. It doesn't matter which one comes out first or second. So this is a combination probability. We are looking for the probability of selecting 2 defectives out of selecting any 2 bulbs. So for our denominator, how many ways can we choose 2 bulbs out of 24 bulbs? When there's no order, we have a combination of 24 choose 2. Now in this particular situation, how many ways can we select 2 defective bulbs? So again, no ordering, it's a combination. There are 4 defective bulbs in there and we are selecting 2. So that would be a 4 choose 2 combination. And then you'd want to either grab your calculator or use the formula to do these, but I'm going to leave that to you and I'm going to skip straight to it. So 4 choose 2, you can calculate that by hand or with the calculator. That's 6 out of 24 choose 2 is 276. And you can reduce that to 1 over 46. And for our last question, they say, what is the probability that at least one selected is defective? So probability at least one defective. That's the same as 1 minus the probability that none are defective. Another way to say that would be to say 1 minus the probability if none are defective. That's the same thing as saying that they're all good. Let's look at that this way. 1 minus then, we would be choosing all good bulbs out of choosing any 2. We have 1 minus then, let's look at this fraction. The denominator is the same as in part A. If we're choosing any 2, we have a combination of 24 choose 2. That's how many ways we can do that. Now, how many ways are there to choose 2, but all good bulbs? Again, it's a combination. How many are good in this box? There were 24 total, 4 are defective, which means 20 are good. So out of those 20, we would be choosing 2. That's how many ways we can choose 2 good bulbs. Again, at this point, you would want to either go to your calculator or pull out the formula for combinations, but we already know that the denominator of this fraction is 276. And 20 choose 2 happens to calculate out to, there's 190. Hence, to calculate this final probability for the probability that at least one selected is defective, we need to do 1 minus 190 over 276, which is 43 out of 138, because you can subtract that and reduce it.